Hello everyone, myself Yutolia. I'm from CSPIT My enrollment number is 24CS019. So today we'll be present our project on finding the largest number possible from a given set of numbers. In this presentation, we'll explore how we can arrange a set of numbers in a particular order so that their concentration forms the largest possible numeric value. We'll explain both the brute force and approach and the greedy approach, compare them, and finally show why the greedy method is smarter choice. So let's come to problem statement. The problem statement is simple but interesting. We are given a list of numbers and our goal is to arrange them in such an order that when we join them together they form the biggest possible number. For example, if our input is 10, 68, 75, 7, 21 and 12, then the largest number we can form is 7, 75, 68, 21, 12 and 10. At first glance, it seems easy, just sort them in descending order, right? But as we'll see next, that doesn't work always. So the objective and importance is first, our primary goal: rearrange given number to form the largest possible concentration when the value through intelligent ordering. Second, competitive edge. Essential problem type in programming competitions, testing understanding of custom sorting strategies. So learning value is demonstrates practical applications of custom competitors and greedy algorithm approaches. So why normal sorting fails? If we simply sort the numbers in descending order, we'd get 75, 68, 21, 12, 10 and 7. When we join them, the result is 75, 68, 21, 12, 10 and 7. However, the correct and larger result is 7, 75, 68, 21, 12 and 10. So what went wrong? The problem is that normal sorting only compares individual numbers, not the effect of joining them. For example, 7 should come before 75 because 775 is greater than 757. Hence, we need a smarter context aware comparison. So, now the first approach is brute force. Our first brute force approach is the brute force method. In this method, we generate all possible permutations of the given numbers, join each permutation to form a new number, and then pick the largest one. This ensures accuracy but is extremely time consuming. If we have just 6 numbers, that's 720 possible combinations with 10 numbers. It jumps to 3.6 million, and with 15 numbers over a trillion. Clearly, this method is not practical for a large input, but it's useful for understanding the problem logic. So now come to the brute force code. Here's the C++ implementation of the brute force method. In the brute force approach, we start by including the required header files like IOStream, vector, and algorithm for input and output operations, dynamic arrays, and utility functions inside the function. For large number brute force, we first convert all the integers into string and store them in a vector called str because concentration is easier with strings. We then initialize an empty string largest to keep track of the biggest number found so far. The vector is sorted initially to ensure next permutation can we generate every possible arrangement of the numbers. Inside a do-while loop, each permutation of the string is joined together into a simple string called temperature. This string represents one possible concentration of all numbers. We then compare temp with largest. If it's greater, we update largest. This process continues until all permutations have been checked. Finally, we return the largest string which holds the maximum possible number formed. In the main function, we pass a vector like 10, 68, 75, 7, 21 and 12 to the function and print the output. The program correctly outputs 7, 75, 68, 21, 12 and 10. But because it checks every possible order, its time complexity is O of n, making it suitable only for very small inputs. This guarantees the correct answer but at the cost of exponential time complexity. So the drawback of brute force is as the number of element increases, the time required grows factorially. For example, for 10 elements, it would take millions of permutations to check. Therefore, although the brute force method works perfectly for small database, it's inefficient and impossible to use for larger input. So we need a better and faster solution. So the approach 2 will now explain Palak.
Hello, myself Palak Donga. My ID is 24CS020. Our second approach is the greedy method using a custom comparator, which is both efficient and elegant. The key idea is simple. For any two numbers x and y, we don't compare them directly. Instead, we compare the concatenated results xy and yx. Whichever combination gives the larger number determines their order. For example, if x is equal to 15 and y is equal to 4, xy is equal to 154 and yx is equal to 415. Since 415 is greater, we place 4 before 15. This greedy decision ensures that at each step we make the locally best choice that leads to the global maximum. This code represents the greedy comparator approach, which is much faster and more efficient than the brute force method. Let's break it down step by step. We start by including the necessary headers: IOStream for input and output, string for handling string operations, vector for storing our list of numbers, and algorithm for using the sort function. We use using namespace std to simplify syntax. Next, we define a custom comparator using a struct. Inside the struct, we overload the function called operator. This allows us to customize how two integers, let's say a and b, are compared when sorting. Inside this comparator, we first convert the two integers into string using toString a and toString b. Then we form two possible concatenations. Value 1 is equal to toString a concatenate toString b, and value 2 is equal to toString b concatenate toString a. The idea is simple but clever. If value a, which representing placing a before b, is greater than value 2 placing b before a, that means a should come before b in the final arrangement, otherwise b should come first. The single line return value 1 greater than value 2 is what makes the comparator greedy. It always picks the locally optimal order for each pair of numbers to eventually form the globally largest number. Next, in the function findLargestNumber, we pass a vector of integers. We use the sort function along with our custom comparator. This rearranges the entire vector based on which pairs of numbers form larger concatenated results. Once sorting is done, we initialize an empty string s and append each element of the sorted vector to it using a simple for loop. This gives us the final concatenated number. Finally, we return this concatenated string as our answer. In the main function, we define a vector of numbers 10, 68, 97, 9, 21, 12 and call find largest number numbers. When the program runs, it outputs the largest number is 99768211210. What makes this approach so efficient is that it avoids checking all permutations. Instead, it uses sorting logic with a custom rule. Hence, the time complexity reduces from O of factorial n in brute force to O of n log n, the same as standard sorting. This algorithm is not just a smart, it's clean, scalable, and elegant, which is why it is considered a greedy algorithm. Now, let's understand how this algorithm works internally with a dry run example. We will take the input 10, 68, 97, 9, 21, 12. Here the goal is to arrange these numbers so their concatenations forms the largest possible number. We start comparing pairs using our custom comparator, which decides order by checking which concatenations xy or yx gives the larger value. Step 1. Compare 9 and 97. Combines them both ways. Xy is equal to 997 and yx is equal to 979. Since 997 is greater than 979, this means placing 9 before 97 gives a larger number. So 9 should come before 97 in the sorted order. Step 2. Compare 9 and 68. Xy is equal to 968 and yx is equal to 689. 968 is greater than 689, which means again 9 should come before 68. So 9 stays at the top. Step 3. Compare 97 and 68. Xy is equal to 9768 and yx is equal to 6897. Since 9768 is greater than 6897, we place 97 before 68. Order so far 9, 97, 68. Step 4. Compare 68 and 21. Xy is equal to 6821 and yx is equal to 2168. 6821 is greater than 2168. 68 should come before 21. Step 5. Compare 21 and 12. Xy is equal to 2112 and yx is equal to 1221. Since 2112 greater than 1221, 21 comes before 12. Step 6. Compare 12 and 10. Xy is equal to 1210 and yx is equal to 1012. 1210 is greater, so 12 comes before 10. After all comparisons are complete, the sorting algorithm arranges the elements in the final order 9, 97, 68, 21, 12, 10. Now we concatenate them. Gives 99768211210. This is the larger possible number that can be formed from the given set. In summary, the greedy comparator efficiently arranges numbers in the perfect order 9, 97, 68, 21, 12, 10, giving the largest number 99768211210. It is simple yet powerful algorithm. The program does not always start with 9 and 97. The sort function automatically selects pairs but always applies our custom rule to form the biggest possible value. The brute force method tries every permutations, giving the correct result, but taking huge time, O of factorial n. So, it's only good for small inputs. The greedy comparator, however, smartly sorts number using a custom rule and achieves the same result in just O of n log n. Both use O of 1 space, but the greedy method is far more efficient and scalable. The greedy approach gives identical accuracy as brute force but in a fraction of the time. In real-world and competitive scenarios, efficiency matters most, and that's why the greedy comparator is the clear winner. This problem has many real-world applications. It is also useful in number arrangement problems, leaderboard rankings, scheduling tasks for maximum profit, and even in data arrangement system that depends on ordering identifiers efficiently. So, it is not just theory, this problem has real practical use. In conclusion, we explored two methods, the brute force and the greedy comparator approach. While brute force builds understanding through exhaustive checking, the greedy method achieves the same result with far greater efficiency. This project reflects how smart optimization turns simple logic into powerful performance. Yug Dholia, who explained the brute force method, and I am Palak Donga, who presented the greedy comparator method. Together, we learned how efficient algorithm design makes all the difference. Thank you.